Next topic is equilibrium of parallel forces. Let's begin. So same thing with the resultant of parallel forces. These are our equations. Fx equals 0, Fy equals 0, but now we have an additional one. Moment is also 0. Okay, so same concepts, but just equate it to 0. Okay, so let's begin. Number 1. Determine the reactions R1 and R2 of the beam loaded with a concentrated load of 1,600 pounds and a load varying from 0 to an intensity of 400 pounds per foot. Okay, so to save time, I'm going to solve this on my own. So please listen to how to solve for these types of equations. So once again, what's the goal? Determine the reactions R1 and R2. Now, if you've noticed, typically for equilibrium, we're solving for reactions. So this R1, this R2. Now, the problem here is we have two systems. We have this system, and then we have this system, right? So first step is to still draw your free body diagram. So I'm gonna start with this one, okay? As you can see, these drawings show or indicate rollers, right? Let's call that. And whenever you have supports, okay, roller is a type of support, there's gonna be a reaction there. So there's a reaction here, okay? And then you're gonna guess the direction. Usually, if your loads are downward, the reactions are upward, okay? Then I'm gonna call this AB. So let's call this point A, this is point B. So this is RA, this is RB, and then we have horizontal, a triangular load. Okay, and so that's free body diagram for the first set. Okay, these are downward. And then here, let's draw as well for the bottom beam. So we have this, we have reactions here, upward, upward, and then since there's rollers here, there will also be reactions here. Okay, now if you decided this is upward, moving on to the next free body diagram is the opposite. So this will now be downward. Okay, and if this is upward, this is also downward. And then we have an external force over here, right? Next, same thing with the previous lecture. You're gonna decide which to start with or which to start with first. If we look here, we have 1, 2, 3, 4 unknowns. And then here, it's only 2 unknowns. So obviously, I should start with this system. Okay, so let's begin. We have a load diagram here. Whenever we have a load diagram, it's best to convert it to a point load, which means to get its resultant. Okay, so to get its resultant, and it's just the area of your load diagram. So that's just the area of your triangle. Okay, so we can just use that in our equation, and then its distance. Okay, it's 1/3 base from the higher end. This is the higher end, so this is 1/3. This entire thing is 12, so this is 12. So it's 1/3 of 12. Okay, and then therefore this is 2/3 of 12. Okay, so 2/3 of 12. Right, so that's your free body diagram. I need to solve for A and B to solve for R1 and R2. So let's begin. Okay, so to solve for A, similar to what you did with parallel forces, we chose moment, or we used moment. Okay, so you can use moment about any of the supports, because remember, if a force passes through your moment center, it's not included in the equation. Okay, so we can try moment at A, okay, and then equate that to 0. Summation of moment at A equals 0, therefore RA, so this is A, this is B. RA passes through A, so ignoring that, move on to the next forces. Next is R. Rotate that about A. That is clockwise, so positive R, and R is just area of your load, so that's triangle, so 1/2 weight, which is 400, times its base, which is 12. Make sure units are uniform, so feet is the same. So 400 times 12. And then next, multiply by distance, so 2/3 of 12, right? Distance from your moment center. So 2/3 of 12. Next, we have RB, rotate about A, that's counterclockwise, so negative RB times distance, 12, equals 0. Then from this, we can solve for RB. RB is 1,600 pounds. Next, to solve for RA, you can just use summation of forces vertical equals 0. So RA minus R plus RB equals 0. Considering R again is 1/2 400 times 12 and RB is 1,600, we can solve for RA, and RA is just 800 pounds. Okay? And then from that, I can now move on to this one. So same thing as before, you're going to use moment to solve for one of the unknowns. Okay? So you can choose either moment at this point or at this point. Okay? But you're going to choose a point that's more convenient. And that point would be here at point B. Why? Because at point B, RB and R2 passes through it. So two unknowns will be removed from our equation. Okay? So summation of moment at B equals 0. So create your computation, R1, rotate about B, that's clockwise, so positive R1. What's the distance? So from A to B, this is 12, this is 1, this is 3. So total distance is 12, 13, 14, 15, 16. So R1 times 16. Next, 1,600, rotate, that's counterclockwise, so minus 1,600 times 13. What else? RA, rotate. So that's counterclockwise. So minus RA times 12. And again, RB and R2 passes through B, so ignoring that, equate that to 0. RA, we already solved for that. That's 800. So therefore, I can solve for R1, which is 1,900 pounds. Okay? And then to solve for R2, you can just use summation of forces equals 0. So R1 upward, positive, negative, minus RA is also downward, so minus RB. Then R2 is upward, so plus R2 equals 0. Considering R1 is 1,900, I can solve for R2. And R2 is just 2,100. Okay, and that's your answer. Okay, so that's number 1 for resultant of parallel forces. Any questions, please answer in the chat. Okay, no questions. Let's move on to number 2. And as you've noticed, it's a bit similar to one of your previous questions, right? So the roof truss is supported by a roller at A and a hinge at B. Find the values of the reactions. So in the resultant of parallel forces, what we solve for is resultant, right? Now, actually, remember when we said the resultant dictates the motion of your system, okay? We know that the reaction of this is somewhere here, right, and downward. So that means your system would move downward. But in reality, that's not the case because of the presence of your supports. So your roller support and your hinge support. And these two prevents the motion of your system. That's why a truss is actually in equilibrium. Okay. Now we want to know the values of the reactions at these supports. Okay. So the solution is almost the same, right? It's still summation of moment. Okay. So as you can see, the solution is already shown. I'll just explain. Okay. So whenever we're looking for the actions, if you've noticed by now, the technique is to use moment about a support. Okay? So if you do that, right, for a roller, the reaction is always perpendicular to the surface. So here it's upward. And then for a hinge, there's always two reactions, one horizontal and one vertical. Okay? As you can see here. But since there's no external horizontal forces, horizontal reaction here is zero. Okay? Next, you're going to use moment. If I use moment about A, we'll encounter the same problem we did in the previous question we're in. We don't know the perpendicular distance, the force to your point A. Okay, so we're going to do what we did previously. We use triangles or right triangles to solve for that value. So we called it X. Okay, so considering this large right triangle, we can use cosine theta, which is 30, equals adjacent, which is 5. This is the adjacent, which is L, over hypotenuse, which is 5. So we have an equation for L. And then next, considering the smaller right triangle, again using cosine 30 equals adjacent, which is X, over hypotenuse, which is L. And then from that, solving for X is 3.75. Okay, so now we have our perpendicular distances. We can continue with our equation for moment. So summation of moment at A equals 0. As usual, I like taking moment on the left support. So begin, 10 passes through A, so ignoring that. RA passes through A, so ignoring that, we're left with 20. And it's clockwise about A, so positive. So 20 times X, which is 3.75, do the same thing. 60 times 5, 20 times 7.5, and so on and so forth. You know the drill. They're all clockwise, so they're all positive. Then equate that to 0. As you can see here at the end, okay, there's negative RB, right? Because if you rotate RB about A, that's counterclockwise, that's why it's negative RB. And then total distance is 15. So from this, we can solve RB, it's 93.33 kilonewton. Okay? Once you solve for RB, we can solve for RA by using summation of forces equals 0. So starting, RA is upward, so positive, and then 10, 20, 60, 20, 20, 10, and 50 are all downward, so negative, and then RB is upward, so positive. And as you can see here, we're always assuming directions for reactions, okay? I assumed it's upward, this is positive, therefore correct assumption, okay? So that's why you're just gonna input 93.33. Solving for RA, you get 96.67, okay? So that's one way to solve for it. But if you analyze, you'll see that 10, 10, 20, 10, 10, 20, 20, 20, 10, the forces above are actually symmetrical. And whenever you have a symmetrical forces about the center, right, we can just add all of that and place it at the center. So adding all of these, you'll get 80, and again applied at the center. So this significantly simplifies our equation. So same step, moment at A, I don't have to solve for X anymore, okay? So 60 clockwise, perpendicular distance 5, and now all we have is 80 at the top, rotate clockwise. This distance is 5 plus 2.5, that's why this is 7.5. And then 50, and then RB, this is upward. So again, that's counterclockwise, that's why this is negative. RB times perpendicular distance 15 equals 0. Therefore, RB is 93.33. Same thing with the previous answer. And then just use summation of forces vertical to solve for RA. Okay. So once again, the solution is almost the same. We're just equating everything to 0 and adding our reactions. All right. So that's number 2. Any questions for number 2? Please answer in the chat. Okay, no questions. Let's move on to the last question I'll discuss for today. Last 2. Okay. Let's try. Number 3, the cantilever beam is built into a wall 2 feet thick so that it rests against points A and B. The beam is 12 feet long and weighs 100 pounds per foot. There's no question here, but the question should have been, what's the reaction at A and B? Okay, so here, this cantilever beam, a cantilever beam is fixed on one end and free on the other. Okay, so this is free, this is fixed. And then as you can see, it's supported at these points. That's all. So we're not given a point load, we're given weight for this beam. Whenever we have weight that is distributed, it's not just pound, it's pound per foot. We need to convert that into a point load. Okay, so that's the first step. So just copy your load for your free body diagram. So this is 2000. Okay, the entire span is, this is 10, this is 2. So the entire span is actually 12. And then weight is always acting at the center of your object. This is a rectangular beam, so center of that is at the center of its span, so it's at 6, right? This is your weight. And that weight is equal to your pound per foot. So 100 pound per foot multiplied by the entire span, right? Because this is just a rectangle, this is the weight. So that's your omega. So 100 times 12, that's 1,200 pounds. Okay, and then we have reactions here. So we have B and A. Again, you're just guessing the direction. I'm gonna guess at B, it's upward. So this is RB, and then at A, it's downward. So that's RA. Again, this is just guessing. And then include. So this is 6, right? Because it's at the exact center. And then this is 2 feet. Then this is 6. Alright, so now we have our free body diagram. We can solve. Again, first step, we can use moment about a point. Okay, so let's do moment about B. If you want to practice, you can start with moment about the other support. You should get the same answer. So I'm choosing B. So solve 2000, rotate about B, counterclockwise, so negative 2000. Perpendicular distance from B is 12. Next, from B, so that's 10. Next, 1200 counterclockwise. Perpendicular distance, if this is 6 and this is 2, therefore this is just 4. RB passes through B, so ignoring that. Next, RA, that's clockwise, so positive RA times 2 equals 0. Solving for RA, you get 12,400. Okay, so by the way, let me know if any of these computations are incorrect. And then to solve for RB, as usual, summation of forces. Okay, 2000 downward, negative 2000 minus 1200 plus RB minus RA equals 0. RA is 12,000. Therefore, RB is 15,000. Okay, and number 3. So almost the same solution as the previous one. Next, I don't think I have enough time. I'll just upload the solution to number 4, okay? Since we only have 3 minutes left. Right, so that's equilibrium of parallel force systems. It's pretty much the same again as resultant of parallel forces. Just equating it to 0, right? So any questions for equilibrium of parallel force systems before I dismiss you? Okay, how about the others? Any questions? I'm gonna upload the answer key to quiz 1 when everyone has answered quiz number 1. There's some of you who were absent last meeting. Some of you haven't answered the quiz yet. Okay? Yes. No. Remember, deadline of, reminders, Coursera deadline is this Saturday. You can upload it as an image, so PNG, JPEG, or PDF. Okay, as long as I can see it in Blackboard. Doesn't matter the format. Okay, so PNG, JPEG, or PDF. And remember, in your screenshot, your name, your score, title of the activity should be shown. Okay, so deadline Saturday. You'll already see it in your week 4. Also, this Saturday, you have your modular exam topic up to equilibrium of parallel force systems. Okay? Yes, you just have to follow the format shown in the syllabus for what to screenshot. Okay? Any other questions in general? So for those who are absent last meeting, you may answer your quiz anytime this week. Just make sure to send me an explanation letter either before or after you answer the exam. Okay, just make sure you send it within the week as well. Right? Okay, no more concerns, clarifications. Okay. So since you don't have any questions, okay, my bad for taking or making the lecture a bit faster. Okay, I hope you're able to understand even though it's a bit faster. If you want, this will be uploaded later on YouTube. So you can just rewatch if there's something that's confusing you, right? Okay, so once again, Coursera, week 1 and 2, and then modular exam, all on Saturday. Open camera, attend the Zoom meeting. Okay? All right, so since you don't have any more questions, you may go. Bye, class.